Hello everybody and welcome back. Today we'll be talking about how to solve problems involving the motion of objects using calculus. This is part of a larger series on the kinematic equations. And although kinematic equations only deal with motion when the acceleration is zero, there are plenty of examples where the acceleration is not zero, and we can solve those problems using calculus, and that's what we'll be talking about today. So let's begin with the problem. We have a cart is traveling with an acceleration, a of t equals 3t squared plus 2t plus 4. So this is the equation for our acceleration of the object, where when t equals 2, so at 2 seconds, the cart is traveling at 22 meters per second. And when time is 0, the cart is at a distance of 1 meter from the starting line. Find the position function. So we can begin by writing out the equation. The acceleration is 3t squared plus 2t plus 4. And so what we have to realize is that acceleration, velocity, and position are all related by integrals and derivatives. So for example, velocity is the derivative of the position function with respect to time. And likewise, acceleration is the derivative of the velocity function with respect to time. So what we can say is that this acceleration equation here is the derivative of the velocity equation. And if we're trying to eventually get to the position function, we just have to integrate this twice, because the integral is the inverse of the derivative. So what we can say is that the integral of a of t, this is just an indefinite integral for now, equals the integral of 3t squared plus 2t plus 4 dt. And what we can use as the power rule for all of these, so we can say that, again, the integral of a of t dt is the velocity, and then we can take the integral. So we can use the power rule. So we can say that t cubed plus t squared plus 4t plus this constant. And we're going to call it constant 1 because there are constants that are going to appear later on. But the thing is that if we have this plus c1 term at the end here, it creates a family of possible curves that could be the solution to this equation, because there are infinitely possible forms of this equation because this constant here can be any number. And so what that leads to is this graph right here. And so this one only shows up to a certain point on either side, but these would continue on both sides forever. And these are the possible curves that solve this solution. And so to solve for C1, essentially what we can do is use our initial conditions. We are given at the beginning that when t equals 2 seconds, our velocity is 22 meters per second. So what we can say is, plugging that back into our equation from before, we can say that 22 equals 2 cubed plus 2 squared plus 4 times 2 plus this constant 1. And so solving this, we get 22 equals 8 plus 4 plus 8 equals, plus C1. And so that's 1620. So 2 equals C1. And so that is our initial condition. And so what we can say is that the velocity function with respect to t is t cubed plus t squared plus 4t plus 2. And so we can do a very similar process, integrating both sides, because again, the integral of the velocity is the position function. And so we get that the position is equal to the integral of all of this. So again, using the power rule, we can say that 1/4 t to the 4th plus 1/3 t cubed plus 2t squared plus 2t plus c2. And so here we have another constant that can be anything. And so that gives us another possible family of curves, this time for the position function. And so as you see, it's kind of this parabolic motion. But we're also given initial conditions at the beginning that can help us solve this. So we were given that the position at time equals 0 equals 1. And so if we plug that into the equation from before with our possible solution, we see that s of 0 is just, that's 0 to the 4th plus 0 cubed plus 2 times 0 squared plus 2 times 0 plus c2. And if that has to equal 1, then all of these terms go away, and so 1 has to be c2. So our final solution is s of t equals 1/4 t to the 4th plus 1 third t cubed plus 2t squared plus 2t plus 1. And so this is our final solution. And so if we look at it individually, this is what it looks like on a graph. And of course, this is position, and this is time down there. And so the motion of our cart moves forward, and it accelerates at this very kind of steep rate. And if we go back to and so here would be a good time to review how position, velocity, and acceleration are related. So you have the position function equals the integral of the velocity. And likewise, you have the velocity from the same ratio equals the derivative of position with respect to time. You have that the velocity equals the integral of the acceleration with respect to time. And therefore, you also have that the acceleration equals the derivative of the velocity. And these are the ratios and how you get from position to velocity all the way to acceleration and all the way back down.